type B circuits. If you know type A and type B circuits, what's happening with Amalia? Just a minute. Okay, whatever we'll do today will be based on type A and type B circuits only. So the first circuit, so you know how to calculate field, how to sorry, not field, how to calculate charge, how to calculate potential, equivalent resistance and equivalent capacitance. Now we have various types of circuits now. So the first circuit on which we will concentrate are basically the circuits in which you are supposed to calculate either equivalent capacitance or equivalent resistance. I won't be calculating potential, charge, energy, or power. We have done those circuits in which you're supposed to calculate charge and potential. Now we'll do circuits in which you're supposed to calculate the equivalent capacitance and equivalent resistance. So let's start with this circuit. Question number 1. And I'll be solving either the circuit with capacitor or with the resistor. The same circuit will be your homework. Like if I solve the circuit with capacitor, then for resistor, it will be homework. I'm giving you this simple circuit. Let's take this simple circuit. This is C, 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 and this is also C. You're supposed to calculate equivalent capacitance across AB. Equivalent capacitance across AB. Now for every type of circuits, we have certain methods to do. Yes, Abdullah, I can discuss doubts after the class. We'll discuss things after the class. So every type of circuits will have certain methods. So let's start with type 1 circuit. Type 1 circuit. In type 1 circuit, to decide whether the given capacitors are in series or not, there is very simple method. If there is no branching, that means your capacitors are in series. This is the series combination. If there is no branching, like this is series, I need more space. I can even draw it like this. This is also series. It's C, it's C, it's C, it's C. This is series. These all are series combinations. There is no branching, that means your capacitors are in series. This is how we decide whether the given capacitors are in series. That's type A circuit. I'm just discussing how to identify whether the given capacitors or resistors are in series or in parallel. Same is true for resistors. Like instead of capacitor, if you add resistors, then this is the method to identify resistors in series. For parallel, they should be connected end to end. This is parallel combination. End to end connection. This is parallel combination. This is parallel. End to end connection. So the first type of circuits are easy circuits. You can just decide whether they are in series or in parallel by looking at the geometry. Just by looking at the geometry, you can decide. So see, for series, there should be no branching. For parallel, there should be end-to-end connection. Now I'm naming these capacitors. This capacitor 1, I say this as 2, this 3, this 4, this 5, and this 6. Now let's decide one by one. Like if I start from this end, then this C, C, and C means 5, 4, and 6. Are they connected in series? You can use your mic now.
Yes, sir.
Yes,
Are
sir.
they connected in series?
Yes.
No. There is
Sir,
branching.
can
Yes,
you
yes.
say the full name? Like which?
This capacitor number 5, capacitor number 4, and capacitor number 6.
Sir, it is like 4 has a combination of series and parallel. When we fix that, then we can say that
Yes.
4,
So 4
1,
is
2, 3,
neither in
4, and
series.
6 are in series.
Which one? Which one? Which one? 1?
4, 1, 5, then 1, 2, 3, 4, and then 6 are
Nah,
in
nah,
series.
nah, nah, nah. See, Ahmed. 5, 4, and 6 are neither in series nor in parallel. First thing, they're neither in series. 5, 4, and 6 are neither in series. The reason is for series, there should be no branch. You can see there is a branch. There's one
Yeah,
branch.
sir.
Due to this branch, 5, 4, and 6 are not in series. They are neither in parallel. So no series, no parallel combination you can't solve from this end. Remember, for these type of circuits, always starts from the extreme end, the next end. If you start from this end, can you decide whether 2 and 1 are in any type of connection, series or parallel?
Parallel.
Parallel.
Parallel, you can check. See, they are
Parallel.
end-to-end connection. C is connected here. These two are connected here. So you can write that these two are connected in parallel. So you can say that C1 and 2,
So,
yes,
so like 1, 2, and 4 will be in parallel, right? Okay,
no, no, because for parallel, you should have end-to-end connection. See, ends of 1 and 2 are meeting over this point. But the end of 4 is not directly connected here. There is one capacitor C, third in between.
okay, sir.
4 would be in parallel if there is a wire coming from here to here. Then, and there is a wire coming from here to here. Then you will say that 4 is in parallel, but 4 is not in parallel. Are you getting the reason, Abdullah, why 4 is not in parallel? Due to this capacitors.
Yes, sir.
Now they are in parallel. When they are in parallel, C12, we can write this as C plus C because in parallel we'll add them up. So C12 will be 2C. Next, what you can do is remove these two capacitors, add a single capacitor in their place. Add a single capacitor in the place. This is this, and this is it. This is capacitor number 3. This is capacitor number 1. This is capacitor number 4. This is 5. This is 6. Now, can you decide which of them are in series and which of them are in parallel?
3 and 1 and
1,
2.
3, 1, 2.
3 and 1, 2 are in series. So if they are connected in series, then 1 by C3, 1, 2 is 1 by C3 plus 1 by C1. So you can say 1 by C312 is 1 by C3, which is 1 by C. 1 by C12 is 1 by 2C. So 1 by C312 is, the LCM is 2C. You can write this as 2 plus 1 is equal to 3 by 2C. You can write that C312 is 2C by 3 now. That's C312 is 2C by 3.
So how did you get that?
Okay, see this 3 and 4. For series, you have to check no branching. So from here to here, is there any branching?
Yes, sir.
No, there's no branching from here to here. Say from this end to this end, there is no branching. That's why I'm considering this from here to here. They are in series C1, 2,
Yes,
and
sir.
C3,
I
3.
understand about the series, but that 1 by 2C.
Okay, this is how we calculate equivalent capacitance in series. For resistors, we can add them up directly, but if you have capacitors, then we add them.
Sir, it will be parallel, right? C3, 1, 2, and 4.
Yeah, they're bad. Ahmed, is it clear?
Yes, sir.
It's not resistor. If they were resistors, then we will add them up in series. These are capacitors, so it's 1 by C1. So you get C312 as 2C by 3. Okay, next thing. I'm removing these two and adding a single capacitor here. So I'm adding them. Yes. C312. This is 4. This is 5, and this is 6. Now, can you find any combination now, series or parallel combination?
Yes, sir.
3, 1,
4
2,
and
3, and
C3,
4
2, 1.
are in parallel.
Ah, yes. 4 and C312. Is it clear for everyone? They are
Yes,
end-to-end connected. So I can
yes,
say that C4 and C312 are in parallel. So I can say that equivalent capacitance is C4 plus C312. Equivalent capacitance is C4. How much is C4? That's C. How much is C312? C312 is 2C by 3. So you can write that C equivalent
5C
is
by 3.
5C by 3. No, it's not yet C equivalent. More combinations. So this is C3124, 3124, 3124. No, in the last step, I can remove both and can add a single capacitor. So that's C5, this is C3124, and this is C6. Now, can you decide how these three are connected?
series.
This is series. There is no branching now. These all are connected in series. So for series, you will write 1 by C equivalent is 1 by C5, 1 by C3124, 1 by C6. So 1 by C equivalent is 1 by C5. What is C5? C5 is C. C1, 3, 4, 5C by 3. So that's 3 by 5C. C6 is 1 by C. 1 by C equivalent is, you can take 5C as common. This is 5 plus 3 plus 5. So it's 13 by 5C. So your C equivalent is 5C divided by 13 now. This is C equivalent, equivalent capacitance, which is 5C by 13 now. Is it clear?
Yes.
Yes, sir.
So this is how you will solve the type 1 circuits. Type 1 circuits are easy because to decide series and parallel, just have to check this geometry. If there is no branching, then there's a series. If they are connected end to end, then they are in parallel. Okay, just note it down. The same circuit can also be repeated through using a resistor.
Sir, that's homework for us, right?
First question I am repeating with both capacitor and resistor. I'll give you more questions or type 1 in homework. First circuit I want you to solve in the class. Abdullah, end to end means there is no other capacitor in between. It could be positive, positive. It could be positive, negative. There should be no other capacitor or resistor in between.
So done.
Okay. Can I change the slide, everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Done, sir.
Okay, solve this circuit. Same circuit, but instead of resistor capacitor, you have resistor. This is R, this is R, this is R, this is R. It should not take more than 2 minutes. Just solve it. Calculate equivalent resistance across AP. Method is same. It's just instead of capacitor, you have resistors. Fast. And report, write your answer in chat room. Huh? Answers?
So can we send all at once?
Yes, yes, I need R equivalent only. I don't need intermediate step. Now you know how to solve these type of circuits. I just need this R equivalent, the final resistance. I don't want intermediate step, but you have to use intermediate step. Otherwise, you can't solve. You can't solve it in one step. Write intermediate steps and tell me R equivalent. Perfect. Ahmed, good. So it's not that lengthy. R and R, they're parallel, R by 2. Good, Abdullah. This is R by 2. (13 R by 5). Sania, you have to take reciprocal. Huh? (13 R by 5). Good. Amalia. Good, Mariam. Sania, just check your answers. Amalia, Mariam, and Shahzada, you are left. Good, Fatma. Sania, check your answer. It should be 13 R by 5, not 5 R by 30. Shahzada, did you went through the recordings of the last lecture?
No, I had vaccine, that's why I can't.
Okay. So, Shahzada, after today's lecture, just go through the recordings of the last lecture. Huh?
Okay.
Whatever we are doing depends on the last lecture only. So you just check the recordings of series and parallel combination of capacitors. Okay, then you
Okay.
can continue in the batch. Then you won't have issues in the batch. Amalia, it should be 13 R by 5. 13 R by 5, not 5 R by 30. 13 R by 5 is the answer. So I'm not solving it. These two are in parallel, R by 2, then R is in series, then the combination is parallel with this R, then whole system is in series. So that's type 1 circuit, easiest circuit. Then we have type 2 circuit. We call type 2 circuits as infinite series. This is given in NCERT also. So when I say infinite series, means you have infinite capacitors or infinite resistors in the circuit. So I'm taking the example of resistor and capacitor will be your homework from now on. So I'm not capacitor, I'm taking resistor. And this thing is going up to infinity. This is 1 ohm, this is 2 ohm, this is 1 ohm, this is 2 ohm, this is 1 ohm, this is 2 ohm. This is infinite resistance. So the first very natural answer of this question is resistance should be infinite. But it won't be. Because this is series as well as parallel combination. In series, resistance increases, but in parallel, resistance decreases. So it's a combination of series as well as parallel. So resistance will increase as well as it will decrease. So the net resistance will not be infinite. You will have some finite resistance. Now see how to calculate the finite resistance for these type of series. This is infinite series. Step 1. I'm writing the step to solve these type of questions. Step 1. First of all, try to find the term which is repeating. Try to find the repeating term. There should be, in infinite series problem, there should be at least one term which is repeating. Here that one term is this term. See, this is repeating. Once you have identified this term, like 50% of problem is solved. First, identify the term which is repeating. Next, in step 2. Now assume the total resistance of the circuit as some R. And how many times this term is repeating? This is repeating infinite times. Remember. Assume that equivalent resistance is R. Now you can assume that equivalent resistance of the circuit is R. That's the equivalent resistance. So what we can do is, we can assume the equivalent resistance of the entire circuit as R. That's the equivalent resistance. So the first two steps are very clear. What we did, we first of all identify the repetition term, then we assume that the resistance of the entire circuit is R. Step 3, that's most crucial. And this is where I will need your logic. If I add 1 to infinity, then it remains infinity only. Right? If I'm adding 1 to infinity, then it will
Yes,
remain
sir.
infinity only. This term is repeating infinite times. If I add one more term into it, will change the circuit, or the circuit will remain same?
Remains same.
Remains
Repeating
same.
again. This term is repeating infinite times. If I add one more term into it, will there be any change in the circuit? No.
No.
There will be no change. So the step 3 says add one more repetition term and equivalent resistance should remain same. That's the main logic. That's the logic. So what we did, we assume that the total resistance of the circuit is R. I add one more repetition term. I add one more term which is repeating. And as we have concluded, it should not affect our circuit. Means even after adding this term, the equivalent resistance will remain R. Because adding 1 to infinity does not change. Is it clear? After
Yes,
this,
sir.
it's pure calculations. Okay, so what I did, I assume that the resistance of the entire circuit is R, then I add one more term which is repeating, and I say if I add this repeating term into the circuit, then resistance will not change, it will remain R as it is. Now decide, is there any series and parallel combination over here?
Yes, sir.
Yes.
Which one is parallel?
2 ohm
R
and
into
R in parallel.
R.
Okay, R and 2 are parallel. Okay. So I should name it as 1, I call it as 2, I call this as 3. Although I can do it in one step, but I want to write steps. So 1 and 2 are in parallel, so I can say that 1 by R12 is 1 by R. We'll do a shortcut trick to calculate this parallel combination, which will be 2 plus R by 2R. So I can write R12 as 2R by 2 plus R. That's a very common mistake while solving parallel combination, that you don't take reciprocal. You take 1 by R2 and start solving it using 1 by R1. Take reciprocal always. It will be 2R by 2 plus R. Now, instead of these two, I can write 2R by 2 plus R. So the circuit reduced to 1 ohm. The value is 2R by 2 plus R is equal to R. And how these two are connected?
Series.
Series.
1 plus 2R over 2 plus R is equal to R. Let's calculate R. It's 2 plus R, it's 2 plus R plus 2R is equal to R. So you will get 2 plus 3R by 2 plus R is equal to R. It's 2 plus 3R is R into 2 plus R. So it's 2 plus 3R is 2R plus R square. You can take it to the left hand side. So it's 0, which is 2R plus R square minus 2 minus 3R. So it's 0, which is R square minus R minus 2. You get a quadratic equation. Get the roots of this quadratic equation. This is R square minus R minus 2 is equal to 0. The roots that I can take are, I can write this as minus 2R plus R minus 2 equal to 0, right? Yes. So the roots will be R minus 2 plus 1, R minus 2 is equal to 0. So you have R plus 1 and R minus 2 is equal to 0. So you get R equal to 2 and minus 1. See, resistance cannot be negative. It can't be negative. So that's not acceptable. The final answer is 2. Equivalent resistance is 2. So this is how we calculate circuits infinite series problem. Instead of resistor, you can get same problem for capacitor also. Same method. Just you know the difference, that in series and parallel, the method of series and parallel are opposite for capacitor and resistor. Is it clear?
Yes, sir.
Yes,
Okay,
sir.
good. Note it down. Then we'll do type 3 circuit. Next, we will do type 3 circuit.
So done.
So done.
Okay, so next is, you noted this slide also? No.
No, sir.
Yes.
Done, sir.
Yeah? Okay. So that's type 2 circuit. Type 3 circuit. See, all these circuits are given in NCERT. I'm not going out of NCERT. For the type 3 circuits, there is not exact name of the circuit, but I'm writing this as use potential divider method. See, what is potential divider method? Let's do these type of circuits with an example. I give you 3 capacitors. How are they connected? These 3?
Series.
Series. Huh? And now? Can't be decided.
Bridge.
No, it's not yet bridge. For bridge, you always have 5. At least have 5. So it's not yet bridge. So for these type of circuits, you can't decide series and parallel by just looking at the geometry. If you look at the geometry, you will never find series or parallel combination. So for these type of circuits, what we do, we use potential divider method. We provide potential. See, I provide some potential VA here. This we have learned while doing potential divider method, division of potential, that points which are connected with the same straight wire are at same potential. Just tell me, if this is VA, will this is also VA?
Yes, sir.
No, there is capacitor. Capacitor will change, it won't be VA. If this is VAC, this is the wire, this is wire, this is wire going, this is wire going, this is straight wire. No break. There's no break, no discontinuity. This is VA. Here also this is VA. Is it clear?
Yes, sir. Yes.
Yes, sir.
I can't say that this is VA. Let's name it something else, VB. If this is VB, see, this is the wire, this is wire, this is wire, this is wire, this is going this way. This
This
is
is also will be.
Now, let's check potential difference across each capacitor. Potential difference across this capacitor is VA minus VB.
Yes, sir.
Potential difference across the second capacitor is VB minus VA.
Yes, sir.
Potential difference for the third capacitor is again VA minus VB. So they are VA minus VB, VB minus VA, and VA minus VB. How they are connected? If potential difference is same, then what type of combination is this? If potential
Parallel.
difference is same,
Parallel.
yes, then they are parallel. If charge is same, then they are in series. This is parallel combination. It's basically this circuit. So your C equivalent will be C plus C plus C, which is 3C. That's the next type of circuit. Okay.
Yes, sir.
Next, you have type 4 circuit. In type 4 circuit, you will use the concept of short circuit. Short circuit. See, first see what do we mean by short circuit. Like if I take a resistor, I can even take a capacitor. I connected this capacitor resistor through the cell. Assume this resistor as a bulb. Assume it as a bulb. You connect it through the cell, so bulb will glow because current will pass through the bulb. But if I connect the two ends of the bulb through this wire, then bulb will not glow because current will come here, it will come here, and then current will come here. Current will not pass through it. Current will not pass through this resistor. Then we will say that we have short circuited this resistor. Short circuited the resistance means connecting both the ends of the resistor with a wire. What's the effect of short circuit on the circuit? No current will flow through the resistor. Entire current will flow through the wire. If this is a bulb, then this bulb will not glow. So instead of resistor, if I connect a bulb, this is cell. This is the symbol of bulb. Huh? This is how we show bulb in a circuit. So if I short circuit this bulb, then this bulb will not glow. Because current is not passing through the bulb. Current is passing through the wire only. Because, no, why current does not pass through the bulb? It's because current always follow low resistance path. The resistance of the conducting wire is low. So that's why current is passing through the wire only, not through the bulb. That's the short circuit. This is how we short circuit the bulb. So how we use short circuit in the circuit? If I give you a capacitor, I connected this capacitor to a cell and I short circuit this capacitor, then you can simply remove the capacitor from the circuit and connect it as straight wire at its place. If I give you a a capacitor in the circuit and I say that this is short circuit, remove this capacitor, replace this capacitor by a straight wire. If I give you a resistor and I say that this is short circuit, remove this resistor and replace it by a straight wire. Because no current will pass through the resistor. No charge will get stored in the capacitor. It will behave like a straight wire. Yes, Noor, but that doesn't matter. VA minus VB or VB minus VR, at least for the calculation of equivalent resistance or equivalent capacitance are same. Is it clear the short circuit, the concept of short circuit?
Yes, sir.
Like if you have fan, you take a wire, you connected the two ends of the fan with this wire, then there's a short circuit. Your fan will not rotate, no current will pass through the fan. All current will pass through the wire and go to the other.
Sure.
And such a large current will flow through the wire that your circuit will blow up. MCB will be, your fuse basically will blow off.
Sir,
Yes.
So here that does not happen.
In India it happens.
Yes, sir.
Yes.
sir, like in type 3 also it is short circuit, right? Like,
No, that's not short circuit. See, for short circuit, there should not be a wire from in between. This wire, due to this wire, charge can come into the circuit. Due to this wire, it's not short circuit. Like if you want to short circuit the two capacitors together, then it should be like in this way.
it's
Right?
same connecting
There
wire.
should be no wire in between.
Okay.
If there is a wire in between, then this wire can give charge to the circuit, can give current to the circuit. Okay,
Sir, but how?
why? Sorry.
Sir, but how, like the current does not pass through the capacitor, it will just directly go from outside, right?
Yeah, it's because current always follow low resistance path. If you compare the resistance of a bulb and the resistance of a conducting wire, when we draw conducting wire in a circuit, that's the ideal wire having zero resistance. So no current will pass through this resistor. Current will try to pass through a path where there is no obstruction. So current will pass through this conducting wire. No current will pass through. The answer is current follows low resistance path always. This is clear from the formula of current also. I is V by R, right?
Yes, sir.
So I is inversely proportional to R. So point at which resistance is small, more current will pass through it. So this is the path, low resistance path. So all current will pass through. Okay, Shadada. Okay. Yes. Can I change the slide now?
Yes, sir.
Yes, sir.
Now, in the next type of questions, you just have to identify whether a given capacitor or a given resistor is short circuit. Be very, very careful while deciding if anything is short circuited. So all capacitors are identical. C, 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 C. This is A, this is B. Let's
Yes, sir.
name them. It's 1, it's 2, it's 3, it's 4, it's 5. Yes.
Short circuit at 4.
Short circuit at 4, right? This
Yeah.
4 is short circuit. So what you can do
So
is,
the 3,
no, the 3 is not short circuited. See, if you want to short
two
circuit
different
3,
lines.
then the two ends of C should be connected with the same wire, but it's not connected here.
Same. Okay.
So now you know that 4 is short circuit. 4 is short circuit. Now, if 4 is short circuited, then simply remove 4 from the circuit. Simply remove 4. This is 1, this is 2, this is 3, this is 5, this is it. So this C, C, C. I remove this thing. I replace it with a straight wire. This is C, this is 5, and this is. Now you know how these first 3 are connected.
They are
Potential
connected.
divider method.
Yes, by
Parallel.
potential divider method, we know they are connected in parallel.
Yes, sir.
When this, and with the parallel combination of the 3, this 5 is connected in series. So this is the equivalent circuit here. So this is C, this is C, this is. These three are connected in parallel, and with their parallel combination, this C is connected in series. C, C, C. So we'll have 3C and this C are in series. So we have C equivalent as 3C into C, sorry. Okay, this is one shortcut method to calculate. If you have two capacitors connected in series, then you can write C12 as C1 C2 by C1 plus C. So you can write 1 by, so I'm writing the full steps here, but you can do it directly also. 1 by 3C plus 1 by C. So 1 by C equivalent is, we can take 3C as common. I take 1 plus 3, it's 4 by 3C. So you can say that C equivalent is 3C by 4. That's the equivalent capacitance, 3C by 4. Yes, is it clear?
Yes.
Okay, just do it.
Yes,
Then we do another type of circuit. Same circuit can be repeated using a resistor also.
So finish.
So, written, can I change the slide?
Yes, sir.
Yes, sir.
Okay, so this is circuit number of type 4 bis over. Then we have type 5th. In type 5 circuit, what we can do is, let's do Wheatstone Bridge. So Wheatstone Bridge is a very special combination of 5 capacitors or 5 resistors. You can make bridge using a capacitor or a resistor. And the speciality of this bridge is, when we connect these 5 capacitors or 5 resistors, no two capacitor or resistors are in series or parallel. You won't find series and parallel combination in Wheatstone Bridge. I'm repeating again, you have 5 capacitors, minimum 5 capacitors or 5 resistors. And the speciality is no two resistors are in series or parallel. No series, no parallel combination you can find in Wheatstone Bridge. So first, see how this Wheatstone Bridge looks like. Then we will see how to solve these type of circuits. You can make the bridge using a capacitor, or you can make this bridge using a resistor, the same thing. So, okay. So this is the bridge. I'm making it with first capacitor first, C1, C2, C3, C4, C5, and this is the cell. This is the cell. C1, C2, C3, C4, and C5. Now, if you closely monitor this circuit, then no two capacitors are connected in series and parallel. Nothing is series nor in parallel. No two capacitors are series or in parallel. This is point A, this is B, this is C, and this is D. But you can solve this bridge if this is balanced. If bridge is balanced, then you can solve it. What do you mean by bridge is balanced? Bridge is balanced means potential at B is equal to potential at D. Potential over these 2 points is same. If potential at B and D is same, that means potential difference across B and D, which is VB minus VD, will be equal to 0. So balanced bridge means potential drop across this C5 capacitor is 0. Means potential difference across C5 is 0. That is V5 is 0. If potential drop across C5 is 0, then charge stored in C5 is 0. Charge stored in C5, that is Q5, which is C5, C5 V5 is 0. So I'm repeating again. Bridge is balanced if potential at B is equal to potential at D. If B and D have same potentials, then bridge is balanced. What will happen if they have same potential? If they have same potential, then potential difference across B and D is 0. Because they are same. For potential difference, we subtract them. Potential difference across B and D is 0. That means potential difference across the C5 is 0. V5 is 0. If potential is 0, that means no charge is stored in the C5. So you can simply remove the C5 from the circuit. The C5 is doing nothing in this circuit. It's just making it complicated. There's no use of C5 in this circuit if the bridge is balanced. So you can remove the C5 from the circuit. Once you remove the C5, the circuit is very easy to solve. C1, C2 series, C3, C4 series combination in parallel. But the question is, how can you decide whether B and D will have same potential? Because in circuits not given, B and D are at same potential. So to decide bridge is balanced or not, we use balancing condition. Shortcut method to decide whether the bridge is balanced or not. And that shortcut condition says if the ratio of C1 and C2 is equal to the ratio of C3 and C4, that means your bridge is balanced. This is known as balancing condition. We will derive this condition using resistor, the next chapter. But for the time being, I'll be using this condition directly. Bridge is balanced only if the ratio of C1 and C2 and C3 and C4 is same. If this ratio holds, then this thing holds. If this holds, then C5 is not doing any, is not useful in this circuit. You can remove the C5. So if bridge is balanced, then remove C5. Remove the C5. When you remove the C5, the circuit will look like a very simple circuit, a very, very simple circuit to solve. This is C1, this is C2, this is C3, this is C4. That's A, that's B, that's C, and this is D. So you can see this C1 and C2 are in series. C1 and C2 are connected in series. C3 and C4 are in series. And the combination is in parallel. You can get the same circuit from resistor or capacitor. Just note it down, that will give you a numerical. Okay. Yes, noted.
Yes, sir.
Everyone.
Yes, sir.
Yes, sir.
Okay. Solve this question. It's a very easy question, huh? Very easy question. This is 10 ohm. This is 20 ohm. This is 20 ohm. This is 40 ohm. This is 5 ohm. This is 10. Calculate R equal. Solve. First of all, check whether the bridge is balanced or not. For capacitor, it was C1 by C2, C3 by C4. For resistors, it will be R1 by R2, R3 by R4. Check whether the bridge is balanced or not. If it is balanced, then remove the C5. Okay, Noor. Good, Noor. Yes, correct answer. Yes, Mariam, it's balanced. So now try to solve the R equal. Get the value of R equal. Amalia, check whether it's balanced or not. Good, Sania. Now get the value of R equal. Good, Amalia. Now get the value of R equal. Mariam, check your calculations once more. I'm making some small mistake. Yes, Abdullah, you are correct. Just check your zeros. Yes, Noor, it can be solved, but not by the usual series and parallel method. You can solve it using Kirchhoff law. You can solve, but not through the usual series and parallel method. You can solve it using Kirchhoff. Good, Ahmed. Right. Sania, Amalia, Fatma. See, balancing condition, to check balancing condition is very easy. R1 by R2 you can calculate. That's 10 by 20, which is 1 by 2. R3 by R4 you can calculate. Sorry, this is R4. R3 by R4 you can calculate, which is 20 by 40, which is 1 by 2. Now, if it is balanced, then you can remove this 5 ohm resistor. R1 and R2 are in series. So you can say R12 is 10 plus 20 equal to 30 ohm. R3 and R4 in series. R34 20 plus 40 equal to 60 ohm. Then you can calculate R equal. No, Fatma. R equivalent will be 1 by R12 plus 1 by R34. So 1 by R12 is 1 by 30. 1 by R34 is 1 by 60. 1 by R equivalent will be 60. So that's 2 plus 1. 3 by 60. Your R equivalent is 60 by 3. It's 20 ohm. Sania, again, you're not taking reciprocal, huh? 0.0, 20 ohm, 20 ohm. Amalia, Fatma, is it clear, Amalia?
Yes, sir.
Yes, sir.
Okay. So that was about the questions on Wheatstone Bridge. After Wheatstone Bridge, I will give you many questions on Wheatstone Bridge. You can have questions on different forms of Wheatstone Bridge. You can get Wheatstone Bridge in many forms. So I will discuss those forms in assignments. Okay. Next is, so we have done Wheatstone Bridge also. After Wheatstone Bridge, the next is type 6 surface. Now, the type 6 circuits are possible only with capacitors. You cannot make these circuits with resistors. And for capacitors, these are really very important circuits. So I call these circuits as problems involving plates. So for problems involving plate, remember that for series combination, opposite polarities are connected. Opposite polarities are connected. So for series, you will decide it through the polarity. If opposite polarities are connected, then you will say they are in series. For parallel, in these type of problems, same polarities are connected. Plates of same polarities are connected. This is how we decide series and parallel combination for these type of circuits. So the first question in this circuit. So first is this. And you should remember that capacity of a parallel plate capacitor is epsilon naught A by D. We'll be using this concept. They're not possible with resistors. They are possible with capacitors. So I gave you two plates. 4 plates. Area of each plate is A. Separation between alternate plates is D. So first of all, you have to identify that how many capacitors we have. Then we will decide whether it's series or it's a parallel combination. Now, to identify capacitor, remember, capacitor have two plates which are oppositively charged. I'm repeating again. One capacitor have two oppositively charged plates. So these are two plates. If I give this plate positive charge, then this will get positive charge. If I give this plate negative charge, then these two plates are negatively charged. So this is capacitor number 1. This is capacitor number 2, and this is capacitor number 3. So you have 3 capacitors. Now you have to decide whether these 3 capacitors are connected in series or they are connected in parallel. See, for the capacitor number 1. So how we decide we have 3 capacitors? We have 2 plates, positive, negative, positive, negative, positive, negative. So 3 capacitors. Now you decide whether they are connected in series or in parallel. I call this plate as X and I call this point as Y. For positive plate of the first capacitor is connected to point X. Negative plate of first capacitor is connected to point Y. Positive plate of second is also connected to X. Negative of second is also connected to Y. Positive of third is also connected to X. Negative is also connected to Y. So all positive at one place and all negative in one place. So how are they connected? Parallel. Plates of same polarities are connected. So we have 3 capacitors in parallel. Now you are supposed to calculate the capacity of each. C1, C2, C3 is epsilon naught A by D. This is basically the parallel combination. This is basically the parallel combination. C1.
So can you explain that again?
Yes, C3. What? How many capacitors we have or connection?
No connection.
Connection. See, for the first capacitor, the positive plate is at X. If I take second capacitor, its positive plate is also at X. If I take third capacitor, then positive plate is also at X. Negative of all three are connected in Y. So all positive at one plate, all negative at one plate, 1 point.
So where are the capacitors?
These are the capacitors. This positive and negative plate is making a this combination of positive and negative plate, you can see.
Yes, sir.
This is one capacitor. This combination of positive and negative, another capacitor. This positive and negative is another capacitor. Okay.
And what about positive of third is connected to X? Where is that?
Yes, this is third capacitor. This is the positive plate of third capacitor. See, where is
Okay.
it connected? X. Ahmed, what about the negative plate here? This is third capacitor, the negative plate. Where this plate is connected?
Y?
Negative of second,
Y?
negative of first.
Y?
So all negative plate at Y,
Yes, sir.
all positive at X. So what type of combination is this?
Parallel.
Parallel combination. You can calculate C equivalent as.
Sir,
Yes, Abdullah.
so only for like parallel C is equal to epsilon naught A by D, or like for series also?
For series also, because this C is epsilon naught A by D have nothing to do with series or parallel. This is parallel plate capacitor. Even if you have capacitors in series, then also it's epsilon naught A by D. Series, this step will depend upon series and parallel combination, how you combine them. Plus epsilon naught A by D. So it becomes 3 epsilon naught A by D. So that is the equivalent capacitance. This is how we calculate equivalent capacitance. Okay, just note it down. I will give one more circuit on this concept. That's the circuit number 1. Fatma, Mariam, is it clear?
Yes, sir. It's clear.
Yes, sir.
This should be very clear that for a pattern to be a capacitor, for a combination of two conductors to be a capacitor, both the conductors should have opposite charge. If they have same charge, then it's not a capacitor. Remember this thing. Both the conductors should have opposite charge. If conductors have same charge, then the system is not a capacitor. Yes, Noor, I'm coming to those questions also. We'll do 4 questions on this concept. It will cover all types of questions. Okay, so see.
So both the conductors should have opposite charges.
Should
yeah?
have opposite charge, yes. If they have same charge, then it's not a capacitor. If they have same charge, then it's not a capacitor. This is a separation between them is D. This plate area is A. This plate area is A. Separation is all D. Calculate equivalent capacitance. First of all, provide charge and try to decide whether these capacitors are connected in series or they are connected. First of all, decide the number of capacitors you have. Then you will decide whether they are in series or in parallel.
Sir, 2 capacitors
Okay.
and they are in series.
Okay. No.
No?
No series.
3 capacitors are there.
3 capacitors. What are the conditions for a system to be a capacitor? 2 conductors having opposite charge.
Yes, sir. So 2 capacitors are there.
Now decide whether they are in series or in parallel.
They are in series.
See, first of all,
Not
we
a
don't have
capacitor.
3 capacitors. We have 2 capacitors. See, first, one plate is positive, another is negative. First capacitor. Both the plates are negative, no capacitor. One is positive, another is negative, second capacitor. So you have two capacitors. Now, write your answer in chat room. Get the value of equivalent capacitance and write your answer in chat room. I need equivalent capacitance now. Answers. Good, Fatma. Good, Abdullah. Mariam, Amalia, Sania. I'm not disturbing Shahzada today. Huh? You've left many classes. Sania, we have two capacitors, not three. Yes, Ahmed, you're right. Sania, we
Sir, I
have two
forgot to
capacitors.
add A over there.
No issues. Sania, we have two capacitors. Huh? And the capacity of both the capacitor is same epsilon naught A by D now. And they are connected in parallel. See, for the first capacitor, positive plate is at X. For second also, positive is at same plate, negative at same point. So these are two capacitors which are connected in parallel. So C equivalent C1 plus C2 epsilon naught A by D plus epsilon naught A by D, which is 2 epsilon naught A by D now. So that is the equivalent capacitance 2 epsilon naught A by D. Okay, after this, next circuit. For the next type of circuits, we will introduce dielectric slab. So if you have dielectric slab, then the capacity is K epsilon naught A by D. So I take two plates. And in between these two plates, I am filling two different dielectrics. I am filling two different dielectrics. Sorry. I'm filling two different dielectrics. So first is having dielectric constant K1, another is having dielectric constant K2, area is A by 2, area is A by 2, separation between them is D. Separation between them is D. You can connect it to the cell. Cell will provide charge, so you can see that this plate is positive. This plate is negative. So you have two different dielectrics. So consider it as two different capacitors. This is capacitor number 1 having plate area A by 2, separation D. Capacitor number 2 having plate area A by 2 and separation D. So consider it as two different capacitors. C1 is K1 epsilon naught A by 2D. Then you have C2, which is K2 epsilon naught A by 2D, two different capacitors. Now, can you decide how these two capacitors are connected series or in parallel?
So why 2D?
It's because A by 2, na, area is A by 2. It's not 2 due to D, it's A by 2 into
Yes, okay.
area is A by 2. How they are connected? They are connected in series or in parallel?
Parallel.
Parallel.
Why they are in parallel, not in series?
Positive is connected to
Positive, positive.
Because of the dielectric
Very
slab.
good. Because positive plate of one capacitor is connected to positive of another. Negative of one capacitor is connected to the negative of another. Means these two capacitors are connected in parallel. They are connected in parallel. Very good. These are the parallel combination of two capacitors, C1 and C2. So C equivalent, yes.
So like for series, it will be like positive to negative.
Yeah.
Okay.
I'm coming to the series next. Huh? K1 epsilon naught A by 2D, K2 epsilon naught A by 2D. C equivalent is epsilon naught A by 2D K1 plus K2. That's C equal. Now, for series, I'll frame this circuit in this way. This is one, this is two plate. This is the dielectric in between the two plates here. This is and this is the dielectric here. Again, I have two capacitors. Now see how they are connected. Plate area A. Separation between any two plates is d by 2. We divide it into two equal parts, d by 2, d by 2. Dielectric constant K1, K2. So again, you have two capacitors. C1 is K1 epsilon naught. Area is A, but separation is d by 2. Take this 2 in the numerator and you will get C1 is 2 K1 epsilon naught A by 2. Similarly, I can write C2 as K2 epsilon naught A by D by 2. This 2 will come to numerator and you will get C2 is K2 epsilon naught A by 2. So now we have two capacitors. But the issue is we have to decide whether these two capacitors are in series or in parallel. So we can do this in this way. Connect it to a cell. This plate will be positive. This plate, this entire plate will be negative. Due to this positive plate, you have some negative charge induced over this plate. And due to this negative plate, you will have some positive charge induced here. So that's your first capacitor. That's positive plate of first capacitor and negative plate of first capacitor. That's your second capacitor. Positive of second capacitor and negative to second capacitor. How are they connected? Positive plate or positive negative or negative positive?
Negative positive.
Negative positive.
Series or parallel?
Series.
Series.
So we can remember this in this way. If dielectric is dividing the area, A by 2, A by 2. If dielectric is dividing the area, then your capacitors are in parallel. If dielectric is dividing the separation between the two capacitors, then your capacitors are in series. That's it. So these are, the combination is this. So you can write 1 by C equivalent as 1 by C1 plus 1 by C2. You can write 1 by C equivalent as 1 by C1 d by 2K1 epsilon naught. It's d by 2K1 epsilon naught A. C2, it's d by 2K2 epsilon naught A. 1 by C equivalent d by 2 epsilon naught A, 1 by K1 plus 1 by K2. So 1 by C equivalent is d by 2 epsilon naught A, K1, K2, K2 plus K1. C equivalent is 2 epsilon naught A by D, K1, K2 by K2 plus K1. That's C. Now, for more numericals, you can just remember this in this way. If the dielectric is dividing the area, then it is parallel combination. If it is dividing the separation, then it is series combination. Just note it down.
So done.
Okay. So can I change the slide now?
Yes, sir.
Yes, sir.
Okay. One last circuit. K1, K2, K3. This is A by 2. This is A by 2. This is D. This is D by 2. And this is D by 2. Calculate. Can you decide which two capacitors are in series and which are in parallel?
Yes, sir.
K2 and K3 are
K2 and
K1.
K3 are in series, and then K1 and K2 3 are
K2
in
3 are
parallel.
in and K1 are
See,
in parallel.
these two are in series because here this is separation which is dividing. And its combination is in parallel with K1. So you can write this in this way. K2 are in series. K1, sorry, K1, C2, C3. So I'm just drawing the circuit. The equivalent circuit is this. C1, not C1, C2, C3, parallel, C1. That's the last circuit. Now we will start current electricity. Solve it and write your answer in chat. Get the value of equivalent capacitance. Yes, answers. Abdullah. Is kitchen. Okay, Abdullah, seems correct. What about others?
So the answer seems big, so I will not type.
Okay, I'm typing, I'm writing.
So,
Okay, Fatima. I think there's some mistake in the denominator. Okay, I'm calculating it. So, C1 is K1 epsilon naught A by 2D. C2 is it's K2 epsilon naught A by 2 into D by 2. C3 is K3 epsilon naught A by 2 into D by 2. Let's cancel it. So now C2 and C3 are in parallel. So we can calculate 1 by C23, 1 by C2 plus 1 by C3. So 1 by C23, I can write as 1 by C2. This is C2. 1 by C2 is D by K2 epsilon naught A. C3 is D by K3 epsilon naught A. So 1 by C23, I can take D by epsilon naught A as LCM common, and I'll be left with 1 by K2 plus 1 by K3. Next, I can write 1 by C23 is it's D by epsilon naught A. We can take K2, K3 as LCM. It's K3 plus K2. So you can write C23 is it's epsilon naught A by D K2, K3 by K2 plus K3. That's C23. Now, once you have C23, so see C23 and C1 are in parallel. So you can write C equivalent as C1 plus C23. So your C equivalent is C1. C1 is K1 epsilon naught A by D plus C23. C23 is this epsilon naught A by D, K2, K3 by K2 plus K3. So it's epsilon naught A by D. It's K2, K3 over K2 plus K3. So for C equivalent, you can take epsilon naught A by D as common and you are left with K1 by 2 plus K2, K3 by K2 plus K3. So Abdullah was correct. Noor solved it further, fine. Amalia was making some mistake. I think. Amalia, your K1 is missing. Huh? Okay, just note it down. So that was the last circuit in series and parallel combination of capacitor.
Set done.
Okay. Everyone have written?
Yes, sir.
Yes, sir.
yes.
Set done.
Okay, good. Okay, so that finished your chapter number 2. And some portion of chapter number 3 also. So the next class I will start